All right. There seems to be a lot of issues when we're trying to do volume by revolution, either discs, washers, or cylindrical shells. And it ends up that the region they give us, instead of being rotated about an axis, either the X or the Y, is rotated about a line. So this video is going to be volumes of revolution rotation about a line not an axis. Okay. Now I'm going to do one example of a disc, one example of a washer, and one example of a cylinder. The main idea I would like you to get out of this video is that all three of these are going to be done exactly the same way, using exactly the same technique, using exactly the same setup. If we utilize this setup, we can solve all of our volume problems, discs, washers, and cylindrical shells. And it works about an axis, but that doesn't seem to be everyone's big issue. Everyone's big anxiety seems to be, what do I do when they're going to make this rotate about a line? Everything I'm going to show you works perfectly well if you rotate it about the x-axis or the y-axis. These steps that I'm going to put forth in this video, and I'm going to do 3 examples, they work for any rotation problem. If you follow the steps, they seem, after you do this 3 or 4 times, the steps are going to seem redundant. It's going to seem like, well, I can now skip this step because I understand that. I would strongly advise you don't skip steps. I would strongly advise you just follow the program, trust the program, and let the program provide you with the information you need to solve the volume problem that you're faced with on either your homework, a quiz, a test, a final exam, an AP test. It doesn't matter where they come from, these steps always will get you to the correct solution. So let's start with a problem. I have a problem here, and it's the functions that I'm given. So let's be our first example. The functions I'm given are y equals the square root of x minus 1. Already we can start feeling a little nervous. We get the vertical line x equals 5. We get y equals 0. And we're going to spin this about x equals 5. Every one of these problems becomes just a little bit easier if you make your graph large enough that you can label everything you want to label on the graph. I know we have this inherent idea of preserving paper, and I've taught this concept to almost, well, more than 2,000 high school students and another 1,000 college students. And it seems to me that the number one priority is, how small can I make this look? That should not be your priority. Your priority should be, can I get the answer correct? Not, can I get 15 problems on the front of the paper? So make your drawing large. You can do 2 of these per page. That's what I would consider to be extreme. 1 per page is fine. You want a large drawing, and you'll see why as we go through the process. So we're going to begin, right? We're going to begin by graphing our region. So here we have our graph, and I'm going to go ahead, because we're going to spin it about x equals 5, and x equals 5 is on the far right-hand side. I'm going to go ahead and move my axis over here so I can allow myself that sufficient amount of room that I was just referring to. Now we have the square root of x minus 1. That's our friend, the square root of x graph, moved to the right one space. So it's going to start here, and we're just going to get the square root of x, and it's going to go like this. Okay. Now, we're going to go about x equals 5, right? So we'll make it a little smaller, and we'll call this x equals 5 right here. This, of course, is the point 1 where we started our graph. Now, our reflection, right? Our reflection is going to be on the other side of this, because we're going to rotate around the line x equals 5. So our reflection is going to sit here. Now, when we're given this problem, I'm going to do this with discs. And since I'm going to do it with discs, first I'm going to silence my cell phone. Since I'm going to do it with discs and not cylinders, I'm going to do a cylinder problem here just in a second. So I'm going to do this problem with discs. So I'm going to draw my representative slice. My representative slice is going to go from the function over to my axis of rotation. So here's my representative slice. At this point, right, this is where I stop and I start. I've done step 1. Step 1 is make a drawing, draw your representative slice. From here, I am now going to come over to my work area, and I'm going to write my volume equals the integral from A to B. I recognize I'm using discs, not washers. So I am going to write that I'm going to integrate the area in terms of y dy. Now we know we're integrating this in terms of y because our partition, our representative slice, our representative rectangle, whichever phrase you use, is perpendicular to the y-axis, or some of us teach it as it's pointing to the y-axis. Since it's pointing to the y-axis, I'm going to put a dy here. Volume, when using discs, is the integral of the area function. Notice I've also put a y here. This is what I referred to earlier in the video when I said this is going to appear to be a bit redundant at times, but it's the redundancy that leads us to the correct solution. So because this is going to be pointing, the representative slice is perpendicular to the y-axis, it's pointing at the y-axis, I'm going to integrate with respect to y. I'm going to tell myself that I need a function for my area with respect to y. Now I'm going to come over here. I can go ahead and draw my disk if that's going to make you feel better. So we have our disk. Now our job when we're doing a disk problem is to determine the area function. And again, I'm going to write down that I'm looking for the area with respect to y. Again, I get the redundancy, trust the process. This is a circle. The area of the circle is found by using pi r squared. I'm going to write pi r squared every time I do one of these problems. Now, my job, as I now accept it, is to find the radius of this disk. That will then go here for r. I'll take this function, I'll substitute into my integral, I'll integrate, I'll arrive at my correct answer. So to review, we do the drawing. We make our representative slice, or our partition, or our representative rectangle. We determine what variable are we going to integrate with respect to based on the orientation of this slice. This slice is perpendicular to the y-axis. I'm going to integrate with respect to y. I indicate that over here to myself that I'm going to integrate with respect to y two ways. I put a dy here, of course, and here I put a of y. I come over here and tell myself I'm looking for the area in terms of y. This is a circle. A circle has an area of pi r squared. So I write the formula down. I find comfort in being able to proceed from this step to this step. This step leads me to this step. If I just continue to utilize these steps in every problem, then I am always making progress. Now, my next job is to find the radius. Okay. This is where things can, for some of us, get a little tricky. We look at our circle and we know that our radius is this distance right there. That is our radius. And depending on the textbook you have, there's a myriad of different ways that they try to tell you to express that radius. I'm going to provide you with a way that always works on discs, washers, or cylinders. It never fails. I call it the bracket method or the 3-bracket method. Notice I have just made a bracket for the radius. I always begin with that bracket. That bracket is the radius. Now I'm going to make 2 additional brackets. I'm going to take the bracket for the radius. I'm going to label this point right here XY. That is a generic point in the plane, so I can label it XY. I'm going to label that point or a point similar to that XY in all 3 of these examples. Again, I know I've repeated myself multiple times, but the process is going to be identical. Now, I've got this point XY. My radius goes from here to here. I don't want to think too hard to try to figure out what that is. So what I'm going to do now is I'm going to draw a bracket from this axis over to my point, and I'm going to ask myself, how far is that distance? Now, this is the point XY. X is our horizontal coordinate. We are moving in a horizontal direction. So this is X. That is my second bracket. This will always work when you revolve around a line. You will always be able to draw 3 brackets. The first one being the radius, the next one being from the point to the axis. We're not going to draw it to this axis. Obviously, we're working in a horizontal manner here. So we're going to go to here. The final bracket, and there's going to be 3 of these, is going to go from the axis to my axis of rotation. And I'm going to ask myself, how far is that? It goes from the y-axis, x equals 0, to the vertical line, x equals 5. This axis, therefore, or this bracket is 5 units long. If we use these 3 brackets, we will always be able to set up a simple equation involving these 3 measurements. It will not always be the case that they will be oriented in the equation as these are going to be oriented in the equation. But if we look at this, our big bracket is 5, our pink bracket is R, our black bracket is X. So the little X bracket plus the little R bracket, so the little X bracket plus the little R bracket equal the big bracket, which is 5. That tells me then that my radius, if I solve this, and this equation will pop out every time you do a problem and you rotate around a line. When I do this problem, I can solve and I get R equals 5 minus X, not rocket science. I can now come back over here where I have set up my equation, and I now know that my area function is pi times R squared. That's going to be 5 minus X quantity squared. This will work every time. Now, several safeguards are built into this process. One of the big mistakes students tend to make is they get this and they take this and plug it back into their integral and they start to integrate. But we have 3 different places on this paper told ourselves we're supposed to be working with respect to y. Here the area function is with respect to y. Here my differential is dy. Here my area function is with respect to y. I don't have a y here. I have an x. It's going to happen every time. That's why we put the y over here to remind ourselves. When I say it's going to happen every time, I mean, we're always going to get this intermediate step where we end up with this expressed in terms of the wrong variable. There's nothing to panic about. We know what x is. We can come right here to our equation. We can square both sides. We get y squared equals x minus 1. And that leads us to x equals y squared plus 1. Now we have our equation for our area. Our area is pi times 5 minus, don't forget our bracket here. This is going to be y squared minus 1, and then we're going to square that. When we simplify this, we're going to get pi. This is going to be 5 minus a minus 1. Oh, sorry, this is a plus 1, isn't it? So let's make that a plus. We'll have to get the problem correct now. Now it's going to be 5 minus 1. That's going to be 4. We have our minus y squared, and we're going to square that. Now we have nothing left to do but algebra and a very simple integral, right? We're going to expand this. This is going to be pi. This is going to be 16 minus 8y squared plus y to the 4th. And now we're going to put this, the area function, in terms of y. It is in terms of y. We're going to put it here, and we're done. This integral is in terms of y. I have to find my bounds on the y-axis. When I look at my original region, we started here. This is the bottom of our region. This is y equals 0. We went to this point right here. This is where x equals 5. When x was 5, 5 minus 1 is 4. Square root of 4 is 2. So this is y equals 2. So those are our bounds. So we have the bounds from 0 to 2. We don't need them until now, so don't worry about them until now. A to B works just fine. We have our function here. We can clearly put the pi out front. I didn't leave room, so I'll just put it here for now. We have 16 minus 8y squared plus y to the 4th dy. And now we have a simple integral, and we're done. We integrate this, we plug in a 2, and we're finished, right? We're finished. If we take a look at what we have here, right? If we take a look at what we have, we are going to integrate this. We're going to get 16y minus 8y cubed over 3 plus y to the 5th over 5, right? And we're going to have our friend pi out here, and we're going to evaluate this between 0 and 2. For all of you people watching this that are taking AP exams, your common denominator is going to be 15. So if you're going to guess at an answer, don't guess at an answer that doesn't have a denominator of 15. Now, it could be the case that the College Board makes one of these cancel, but that's not going to happen. The common denominator is going to be 15. Now, the answer, I'm not going to do the arithmetic here, right? I'm going to stop at this point and let you continue. But when you get all done with this, the answer turns out to be 256 pi over 15, right? Because, well, I feel like Sheldon on Big Bang if I don't finish the problem. So we're going to have 32. This is going to be 8 times 8. That's going to be 64 over 3, right? And here we have 2 to the 5th. That's going to be 32 over 5. So again, our common denominator is going to be 15. This is going to be 32 times 15. We'll just write it like that and hope something good happens for us. Here we're going to have 64 times 5. And here we're going to have plus 32 times 3, right? And all this is going to be over 15. Well, I don't know how you are at arithmetic. This is 32 times 2, right? So this is 32 times 2 times 5. This is 32 times 10. This is 32 times 3. So we have a 32 times 7, right? So here we have 32 times 15 minus, here we have a 32 times 10 negative plus a 32 times 3 positive. That's a 32 times 7. This is all over 15. Let's don't forget our pi. So what we really end up with here is 32 times 8, right? Over 15 with our pi. 8 times 2 gives us our 16. Carry the 1, that's 25. And we get 256 over 15 pi. Right? If you didn't like what I did with the 32s and kept everything in terms of 32, just, multiply it all out and subtract. The key idea here is the process, and we're going to do this process in the next 2 examples. We're going to draw our picture. We're going to look at our representative slice, nothing more than this green horizontal line. That's going to lead me to my integral, which I'm going to write in a general manner in terms of the function, the variable, pardon me, that I want my function expressed in terms of. That's going to lead me over here to my area, because in this case, we're doing disks, and when we do disks, we have to integrate the area. I'm going to express my function here. I'm going to say it's a circle and it's pi r squared. Then I'm going to proceed. I'm going to solve this. It's going to be solved in terms of the incorrect variable. That's okay. It's 100% expected because my bracket method gives me that. That gives me a simple equation that I can use to find the radius. Once I've found the radius, I'll substitute my correct variable in place of that by solving one of my given equations for that variable. I will do my arithmetic or my algebra, depending how you want to describe this, and then I will integrate and not mess up my fractions so I get my correct answer. All right, so this is disks. We're going to do a washer problem next. It's going to be very similar in the context of the structure of the solution is going to be exactly the same. All right, I'm going to pause the video. I'm going to erase the whiteboard, and I'll be right back. Okay, I've erased the whiteboard. We're now going to do another problem. We're going to use exactly the same steps because there's no reason to use anything other than one method to solve all of these problems. So we'll write this problem down. It's relatively simple. We're going to have the function y equals x squared, just our basic parabola. We're going to have the line y equals 1, and we're going to go about y equals -1. Again, we're going to write the problem down. We're going to proceed to make a drawing that is a sufficient size to allow us to label all the things that we labeled on the last drawing. We're going to want to label those. And if this is a washer problem, usually we end up having to label twice as many things on that drawing because we have our outer area function and our inner area function, each of which are going to result in us drawing 3 brackets. So bigger in terms of the sketch is better. So we draw our sketch. We anticipate that we're spinning around y equals -1. And so we know we're going to need more room down here. Now we're going to have our basic parabola, right? So that's going to be here. Now we go to y equals 1. We have our parabola, so that just goes over 1, up 1, over 1, up 1. And then we have y equals 1 across here. Okay. Now our axis of reflection is not the x-axis, right? Our axis of reflection is the line y equals -1. It's down here. So we're going to spin about this line. Remember, we do the drawing. We haven't written anything else down. We are just focusing on the drawing. If we put our reflection down here, our reflection doesn't start here, right? This is our axis of reflection. So our reflection is going to start here. And so we're going to get our basic parabola down here like this. And this is going to be our reflection of this parabola about our axis of rotation. We draw a representative slice, a representative rectangle, whatever we want to call it. I'm going to choose to use washers here. If I were to choose to use cylindrical shells, I would be going from the function to itself. That's one of those cardinal sins we try to avoid. Of course, we could just multiply everything by 2 and go from this line over and use shells. That's not what this video is about. It's not about shortcuts and easy ways, or what I would consider, truthfully speaking, is the teacher trying to make a problem that doesn't have to be complicated more complicated by trying to simplify the problem in the first place. Just do what you've been given. We are going to do washers. That means my representative slice is going to go this way, and the corresponding slice is going to be here. At this point, I am ready to write down my integral, because I can see that this slice is perpendicular to the x-axis. I can see that I'm going to use washers. I know that the formula for washers is volume equals the integral from a to b of my outer area. It's going to be in terms of x this time, because again, my slice is perpendicular to the x-axis, minus my inner area. That is also going to be in terms of x. And I'm going to put dx right here. The same thing we did in the previous example, all of this to make sure that we understand that when we're done working over here, our functions must be in terms of x. I'm not going to worry about my bounds. They'll come to me later. Right now, I'm just going to take the process and trust in the process. Draw your sketch. Draw your representative rectangle or your slice or partition, whatever your textbook tends to call it. From there, determine if you're using x or y, which of those two variables is it going to be, and write down the general version of your integral. Now we have a job to do, right? Our job here is, we can draw, if you want to, we can draw in our washer. All right, so the inner disc is going to look like this, and our exterior, our outer disc is going to look like this. All right. Now, what are we going to have to do? We're going to have to find our outer area in terms of x, which we know is pi r squared, and we're going to have to find our inner area in terms of x, which we know is pi r squared. And at the beginning of the video, I told you that it's not going to be very long after you follow this process that you're going to be tempted to begin to skip steps and just go, well, I see what's going to happen. We write this every time, yada, yada, yada. Do that at your own peril. If you write the steps and follow the steps, the answer always appears. When you start skipping steps, I can't make any guarantee that you're not going to get lost. So I'm looking for a function in terms of x. I have to find my outer radius. I'm looking for a function in terms of x. I have to find my inner radius. We can even go as far as to write an O under here and an I over here, if that's going to help you. They are not the same radius, right? You have an outer radius and an inner radius. Now, this problem I picked on purpose. I'm not going to describe it in any other manner other than truthfully. I picked it on purpose because I only need to use the 3-bracket method once on this problem. On a lot of problems that you're going to do that involve washers rotated around a line, you're going to need the 3-bracket method here and the 3-bracket method here. Why did I not do an example like that for you? Well, the 3-bracket method doesn't change. It works every time. If you have to use it once, use it once. If you have to use it twice, use it twice. The process doesn't change. However, when you do have to use it twice, your drawing becomes quite busy. And I didn't want this video to become confusing to you based on the number of brackets that were drawn over here. So why do I know I don't need to use the 3-bracket method twice, even though it's spinning around a line? Well, let's take a look at what happens when we try to identify our outer radius. Our outer radius goes from there, this point right here, right, which we're going to call XY, just like we did on the disk method. We called it XY. We're going to call it XY here. But when we draw this radius, it goes from here to our axis of revolution. We'll draw it over here out of the way. This is our outer radius. Now, if we take a look at our outer radius, we see the special nature of this problem. And this is, again, why I picked it, not to cheat you of the opportunity to see the bracket method twice in the same question. Again, I did that just to try to keep the drawing a little neater. When we take a look at this, we go from a horizontal line to a horizontal line. It does not matter where I draw this slice, this green slice, no matter where I draw it, I'm going to draw these and then erase them. But if I draw it here, the radius is going to go from this point to this line. It's going to be the same distance. If I draw it here, the radius is going to go from this point to this line because they're both horizontal lines. That distance is going to be a constant. Now, that does not happen on every problem of this nature. It could have been the case that this top function was another parabola. And then we would have to use the 3-bracket method twice. But here we're blessed by the question that we were given. We can see that this is the line, right? We can do our algebra and we know how to graph. We know this is our basic parabola. We know this is the point 1, 1 right here. So we know this is the line y equals 1. Our axis of rotation is the line y equals -1. So this radius is a constant. It equals 2. It's going to be 2 everywhere. So when we come over here to our area function for our outer radius in terms of x, we're going to have pi. We plug in our outer radius, which in this case is a constant, and we just get 4 pi. Now, the inner radius is not going to work out like that. The inner radius goes from a function which changes its y value as its x value changes. So we're going to need our 3-bracket method. So here we go. This is the same 3-bracket method we used on the last example. It's going to be the same 3-bracket method we use on the next example. We start by labeling the point xy. It's the same x is here, a different y. If that's going to bother you, call this y sub 1, call this y sub 2. It's not important because they're not going to flow into both of these equations simultaneously. But if that is something that's going to cause you some kind of mental grief, then just label one y sub 1, label the other one y sub 2. Now, we're going to draw our brackets, right? Our radius goes from here to here. This is our radius. We do not know how big that is. We do not know how to express that. So now we're going to draw our other two brackets. Those brackets are going to go from our axis to our axis of rotation, just like they did in our previous problem. This is the line y is 0. This is the line y is -1. So we know that distance is 1. It goes from a horizontal line to a horizontal line. That distance never changes. Our third bracket goes from our point to our axis. That distance, this is the point xy. This is the vertical distance above the x-axis. We have been taught correctly that we refer to that as y. That is y units up. We now have three variables just like we did before, and we know which two little brackets add to which big bracket. In this case, the two little brackets are the black ones. We have y here and 1 here. So we have y plus 1 equals our bigger bracket in this case is r. So we don't have to do any algebra this time. We can see r is equal to y plus 1. Now, that is our inner radius. We're going to come over here. We're going to substitute this in. I'll move it a little less so we can save ourselves the room. We're going to have pi. We're going to have y plus 1 quantity squared. Because remember, it's a circle. The area of a circle, pi r squared. Now, I can expand this now if I want. I can expand it later if I want. What I need to make sure I realize, however, is I'm not done. This says my area function has to be in terms of x. I currently have my area function in terms of y. So this is not finished. I need to change my variable. I am told by my equation here, based on the fact that this point xy is on the parabola, right? It's on the brown parabola. That parabola has the characteristic that y is equal to x squared. So I can come over here, and I'll keep sliding left to make more room. We have pi. We know y is x squared. Here's our plus 1. We're going to still square it. Now we can do our algebra, right? And if we do our algebra here, we get pi. We get x to the 4th plus 2x squared plus 1. We have both of our area functions. Again, from the top, we drew the picture. We didn't write anything down but the problem. We drew the picture. We drew the reflection. We drew the representative slice, or the partition, or the representative rectangle. We didn't draw the washer. We didn't draw any circles. We didn't get confused with anything. We identified that this is perpendicular to the x-axis. That was the key that unlocked the door that said to write it in this form, because it's a washer. Outer area in terms of x minus inner area in terms of x dx. I then expressed what I needed to find. I needed to find my outer area function in terms of x, my inner area function in terms of x. I wrote down, because it's a circle, pi r squared and pi r squared. Only then did I come over here and start filling in my picture and looking for the outer radius, which in this case turned out to be a constant, and the inner radius, which was not a constant because it lives on this curve. So therefore its y value changes as its x value changes. And I used my three brackets, same three brackets I drew the last time. There's always going to be one big one, two small ones. The two small ones add up to the big one. I don't pay attention to, is the big one going to be the radius? Is the big one going to be the constant? Is the big one going to be the y? I don't care about that. It will solve itself. I just draw them. I build my equation and I solve it for r. Sometimes like this, it's already solved for r. Other times, I have to move one number to the other side. I then go over, substitute that into my equation. It's always going to be in terms of the wrong variable. That's expected. That's what's supposed to happen. It's why we put the x here to remind ourselves we're not done. We use our function that was given to us to get ourselves in terms of the correct variable over here. We do our algebra, we plug it in. So what do we have now? Now we have an integral. Only now do I worry about the bounds. Now the bounds here are in terms of x. This parabola goes from -1 right here to +1 right here. We all know that we could integrate this from -1 to 1. That's going to be perfectly fine. But we recognize the symmetry of the situation, the symmetry of the shape, the symmetry of the solid that we have here. And we understand that if we just use half of this, we can integrate from 0 to 1. And as long as we remember that that's only half of it and put a 2 out front, we can save ourselves a little bit of work. Now, our outer function is written right here. It's 4 pi. So we can just put that here minus our inner function. It's written right here. So that's going to be pi times x to the 4 plus 2x squared plus 1. And then we have our friend dx. We can put the pi out in front, of course. Here we're going to have a 4 minus a 1. That's going to give us a 3. Then we're going to have a minus x to the 4th. And we're going to have a minus 2x squared dx. If we go ahead and integrate that, we're going to have 2 pi. This is going to be 3x. This is going to be x to the 5th over 5. And this could be minus 2x to the 3rd over 3. We're going to evaluate that between 0 and 1 because of the 2 we put out front. That gets us now 2 pi times 3 minus 1/5 minus 2/3. So we end up with 2 pi. Our common denominator is going to be 15. This is going to be 45. 15 times 3 minus 3. 5 into 15 is 3 times 1 is 3. 3 into 15 is 5 times 2 is 10. So we have 45, we have 35, we have 32 times 2. And so we have 64 pi over 15. Now, this process, I'm going to do another problem right now. I'm going to do a cylinder problem with this. I don't want to just leave you hanging and have you have to, on faith, believe me when I tell you the process works for all of the problems. It will. This process works when you rotate around an axis. Please don't misunderstand and think that if you're rotating around an axis, you have to do something different. No, you do not. The only difference when you rotate around an axis is you don't need the brackets. You would still make your drawing. You would still draw your representative slice. At that point, you would write down your integral. If it's washers, the integral is going to look like this. If you're going about the x-axis, if x is your variable, if it's y, well, then it's going to look like y. The only difference if you're going around an axis is that when you come to this step over here, you're still going to write this down. You're going to do exactly what we've done here. It's just you're not going to need the brackets to figure out your radii. So this process works on all of these problems, all of them. I don't care what you rotated around, this works. I don't care if you use washers, discs, or cylinders, this works. You don't have to think about anything else. Just follow these steps. All right, I'm going to pause the video, erase the board, and I'm going to do the cylinder problem. Okay, we've erased the whiteboard. We've done a disc problem. We've done a washer problem. Now we'll work out a cylinder problem. So the functions we're given here are x equals, just in case you didn't think I could graph sideways, y squared minus 2y. We have x equals 3. And we're going to go about y equals 1. Okay, so now we're going to do what we'll make our drawing. Y equals 1 is above the x-axis, so we're going to have to leave some room up there, right? So here we are. Now, this is, of course, y times y minus 2. So the y-intercepts are 0 and 2. This parabola opens to the right because the y value is positive. We know the axis of rotation is right here because it's halfway between the intercepts because of the symmetry. So we have a sideways facing parabola. Now, one of the things that drives students a little crazy when they begin these kinds of problems is a drawing like this, where, in my opinion, the author has not been as thorough in their presentation of the problem as they should have been. If we were to draw this parabola, right, this is a 1, yes, this is a 1. So because that's a 1, our parabola goes over 1, up 1, over 2, up 4, right? That's how a basic parabola works. What I'm saying is the vertex is right here, right? It's over 1, down 1, over 1, up 1. This is the vertex of our parabola. So our parabola goes through here like this, and it goes down here through here like this. Well, this is a bit disconcerting because if you think about this, we're supposed to be rotating this around the line y equals 1. Well, the line y equals 1 is the axis of our parabola. Now, when we get a drawing like this, the author expects us to apply some common sense. The theory on the axis of rotation, or the rotation by volumes by rotation, pardon me, is that when you spin it, you're going to spin it 360 degrees, and you're not going to clang one part into another part of your solid. See, if I were to take this entire parabola, as I have it represented on the whiteboard right now, and if I were to spin it 180 degrees, this piece would be here, this piece would be back here. I would have the solid that came across the surface, above the surface of my whiteboard. That would be generated by this. This would generate the solid that would be on. I would have a full solid represented, but I would have only rotated 180 degrees, or pi radians. If that's the case, the author assumes that we are wise enough to realize they did not mean for us to draw the entire parabola. So that's on us. Now, if your textbook is written a little bit better than this textbook, perhaps they would have made that a little clearer. But our, right, this is x equals 3. So that's 1, 2, we'll just call this 3 right here. Our region that we are supposed to rotate is this region right here, okay? And we are supposed to rotate this around the line y equals 1. So we have done exactly the same thing here that we've done in the previous problems. We've drawn our region. Now, we can draw, right? We can draw our reflection. Our reflection is going to go down here like this, right? This is going to be our reflection right here. Now, we can do this problem with discs. If we draw vertical lines, discs work perfectly. But I'm going to draw horizontal lines and do this problem with cylinders. Because why? Well, just because I've already done a disc example. Let's do a cylinder example. So here's my representative slice. Here's my corresponding representative slice. When I spin this slice, I generate a cylindrical shell that looks like this. All right. Now, what does that mean? Well, it means my approach when it comes to writing my integral is going to change. In the past, our integrals have been volume equals the integral from A to B, and then we had our formula written down that was either area, we're going to integrate area, or we're going to integrate the outer area minus the inner area. Here, however, we're doing a cylindrical shell. Cylindrical shells always mean we need the circumference, we need the height, and we need the thickness. I'm not going to explain the method of cylindrical shells. Hopefully your teacher's done that for you. But these are the three things we need. One of them we already know. Our representative slice is this green slice here. It is perpendicular to the y-axis. So our thickness is going to be in terms of dy. So we know that our integral for volume is going to be in terms of y. Now, instead of going over here and looking for my area in terms of y, or my outer area and my inner area in terms of y, I don't have that because I'm doing cylindrical shells. I'm going to look for my circumference in terms of y, which we know the formula for circumference is 2 pi times r. And I'm going to look for my height in terms of y. And I'm again going to put the y here and the y here to remind myself that no matter what I obtain in solving these two equations or these two missing components of my integrand over here, they have to be in terms of y before I can put them over here. Again, I get the redundancy, but trust the process. All right, so we're going to start with circumference. Circumference has a variable of the radius. The rest of it, 2 pi, that's obviously a constant. So what do? I come over here and I tell myself, okay, my radius goes from here to here or from here to here. And we're going to use the same steps we've used in the past. We're going to identify this point as x, y. And we're going to ask ourselves, how far is my radius? Well, I don't know how far that is. This is clearly the radius, so I'm going to label that r. Then I'm going to go from here, my axis of rotation, to my axis. I know that distance is 1 because this is the line y equals 1. This is the x-axis, so that is 1, right? And now I go from here down to my axis and I ask myself, how far is that? Well, this is a vertical height. This is the point x, y. So this is y. And now again, I have my 3 brackets. In this case, I have r. The little bracket is r. Another little bracket is 1. And that equals the big bracket, which is y. And so I'm able to solve for my radius. My radius is y minus 1. Now I'm going to substitute that in here. This is going to be 2 pi times y minus 1. Now, this is a y, this is a y, this is a y. So I'm done. I don't have to do any substitutions. I have what I need. It's written in terms of y. I'm ready to put it here. But I need my height. I need my height. Well, the height, get this pink pen right, the height is going to go from here to here. This is the point xy. This is also the point xy. Now, they're not the same x, right? This x is in the second quadrant. This x is in the first quadrant. We could call this x of 1. We could call this x of 2 if you want to think about it that way. My height is going to be, in this case, it's going to be x sub 2 minus x sub 1. Now, my job, of course, is to figure out who those x's are. Again, I need it in terms of y. This is in terms of x. But I know what those two x values are. This one is a vertical line. This is the line, right? They told us this line was x equals 3. So x sub 2 is going to be 3. X sub 1 lies on this curve. And I know on that curve that x is equal to y squared minus 2y. And now I have both my circumference in terms of y and my height in terms of y. So I can substitute those back into my integral. I can also go ahead and put in my values for y. When we look at this, right, when we look at this picture, where does y begin and where does y end? Well, remember our original, right? Our original region is this half of the parabola right here. It begins at a lower bound of y is 1. This is x is 3 right here. Well, when we plug a 3 in here for y, we get 9 minus 6. So this is the 0.33. So my integral is going to go from 1 to 3. 1 to 3. My circumference is given to me over here. It's 2 pi times y. My height is given to me over here. It's 3 minus y squared minus 2y. Then I'm just going to slide my dy down here. So again, we followed the same process. We drew our picture. We drew our representative slice. We noticed our representative slice was perpendicular to the y-axis. It pointed at the y-axis. It passed through the y-axis, whichever of those you want to use. That told me that I knew I was doing a cylinder problem. I could see it from when I had drawn the picture. It was going to be a cylinder. Cylinders are circumference, height, thickness. I wrote that down. I don't preach, 2 pi x f of x dx, 2 pi y f of y. Why worry about that? Why don't we write down the fact it's going to be circumference, it's going to be height, and it's going to be thickness, and let the variables work themselves out. Let's use one method that works for all the problems. Instead of going, well, this is an x, this is a y, no, it's just too many things to think about. I then came over. I know the circumference of a cylinder, pardon me, is 2 pi r. Well, that's the circumference of a circle because that's the base of the cylinder. So 2 pi r. So I wrote that down. I did my work to find r. In this case, to find r, I had to use the 3 bracket method again. It's okay. It doesn't turn out to be a very hard equation. Then I have to find my height in terms of y. I noticed the height went from this point to right-hand side to left-hand side. It went from this x value, which I called x sub 2, to this x value, which I called x sub 1. X sub 2 minus x sub 1. I came over to my original problem and found out who x sub 2 was. I found out who x sub 1 is. I write them down. Now, there's a lot of algebra to do over here, right? There's a lot. We can take the 2 pi out. We have to integrate from 1 to 3. We have y times 3, so that's going to be 3y. We have a minus y times y squared, that's going to be y cubed. And we have a minus y times 2y, that's going to be minus 2y squared dy. And so we have to integrate this and solve to get our answer, all right? I'm not going to go through the algebra. I've done 2 integrals for you. This video is not about integration. This video is about the process. The answer to this, if you do it, is 8 pi, okay? So you should be able to integrate that, plug in the 1, plug in the 3, multiply by 2 pi, you should get 8 pi. All right, I hope this video helps. This process always works. You don't need to worry about, is it a disk problem? Is it a shell problem? Is it a washer problem? Do I spin it around a line? Do I spin it around the x-axis? Do I spin it around the y-axis? How is my axis of rotation related to my graph, related to my axes on just the coordinate plane? All of those variables are taken out of play if you just follow this process. I hope you find this to be a successful and seemingly, possibly, hopefully, enjoyable way to do these problems. Enjoyable in the context, of course, that you get the correct answer, not that any of us are choosing to do this for fun. All right, have a pleasant day. I hope this pays off in the end and leads you to some positive results in terms of your grades and your homework.